Let's begin the exploration on static indeterminacy of frames. We now are already familiar with what is meant by static indeterminacy. That is the number of support reactions and internal member forces that are in excess of the number of static equilibrium equations, what we mean by static indeterminacy. We know that the way we approach external static indeterminacy in case of beams, frames, and trusses, or at least I can say beams and trusses, are similar, whereas the internal static indeterminacy differs based on the number of internal stress resultants. Okay. To put otherwise, in case of beams, we have seen that the internal stress resultants are shear force and bending moment, whereas in case of frames, we have something additional called axial force. It is actually helpful to contrast between how a truss and a frame behaves, and we can compare the formulas what we use to determine the static indeterminacy as well. So toward the same, we're going to see these two figures here. In figure 1, we have a truss which is in which the members are connected by pin joints. And in this case, that is in figure 2, we have the same configuration, the same support. The only difference is in this case, it's a frame because these joints are rigid here. Okay. So that's the first difference between a truss and a frame. In a truss, the joints are thin, whereas in a frame, the joints are rigid. Okay. The second difference is in case of truss, the loads are only allowed to be applied at where the joints, such as what we see here. I mean, we have a force divided by P being applied at this particular joint B. But this is not the case when it comes to a frame. It's not necessary that the loads are applied only at the joints. The loads can be transversely applied anywhere else. For instance, we have a load transversely applied to this particular member connecting this joint A and B. Okay, that's the second difference. Loads act not merely at joints. The third difference is what I have already told. In case of a truss, the only internal stress resultant is what? The axial force. Whereas in case of frame, we have axial force, shear force, and bending moment. These are the three internal stress resultants. That means if I cut any member like this or like this or like this in a frame, these three internal stress resultants are there. Finally, in terms of stability, if we talk, the stability of, particularly the internal stability of a truss is related to what is called triangulation. But this is not the case when it comes to a frame. That means it's not necessary that the frames should be triangulated so as to have internal stability. Fine. So for instance, we have a particular frame here that is seen in figure 3. Here we don't see any triangulation. However, this particular frame is stable. Okay. So triangulation is not a necessary condition for the frames to be stable. So these are the four differences that exist between truss and a frame. Next, what we are going to see here in this figure 4 and 5 is the deflected shape of these two structures, that is a truss and the frame, because of the load supply. This helps in understanding something more about the way joints behave. Okay, so if we just consider the first one, we are just going to consider this particular joint B, and the exaggerated views are shown underneath. If we consider what happens with a truss, just we need to understand what is this theta 1, theta 2 first of all. If theta 1 represents the angle between these two members AB, these two members I mean AB and BC, if theta 1 is the angle between these two members before loading, and once after we apply the load, the same angle between, the angle between these two members, the same members becomes theta 2. Okay. So if that is the case, when it comes to truss, these two angles will not be same. That is, the angle between two members connected at a pin joint changes once the load is applied in case of a truss. However, in case of frame, these two doesn't differ. To put otherwise, the angle between any members connected to rigid joint is being preserved even after deformation, that is even after loading. That's what I mean here by theta 1 equal to theta 2. Okay. And apart from that, we do see something extra here. That is, I have also shown the internal stress resultants. In case of the truss, the internal stress resultants are only going to be these axial forces FUB and FBC as we see here. However, if you consider the frame, we can see these triads wherever we make a cut across any member. There is going to be axial force, there is going to be shear force, and there is going to be bending moment. Okay, so I can't keep on telling this. Just bear in your mind that three internal stress resistance are being there in a number contained in a frame. Okay, so that's what I have indicated here. And finally, I can say this detail otherwise. I can say that in a truss, the joint permits relative rotation of the members, whereas in a frame, it doesn't permit relative rotation of the members connected at a rigid joint. Fine. And we also need to see how we are going to use the formula for static indeterminacy. So in order to do that, it is helpful to have a look again at the formula related to the truss, and then we will move on to the frame. Okay. In case of truss, we had this formula already, 1m plus r minus 2j, where this 1 denotes that every member contains an axial force. If we compare this to the formula what we have for the frame, the formula is 3m plus r minus 3j. We have 3 in front of m here. Here, this 3 indicates that every member contains axial force, shear force, and bending moment. Okay. Next is R. This remains same, just that we are going to count the number of reactive components there. In case of truss as well as frame, the same happens with the beam. Okay, so it doesn't change. And then finally, we have this 2 in front of J. Here, this 2 is stands for, this 2 is for two equations of static equilibrium being applied at every joint, pin joint of a truss. Okay, if we contrast this 2 with this 3 here, this 3 is for three equations of static equilibrium being applicable at every rigid joint. That is, we have this extra sigma mz equal to 0, so this 2 becomes 3 here. So that's all. We are going to use this formula 3m plus r minus 3j. That's the reason why I contrasted this formula with the earlier one, what we know regarding a truss. Okay. The final comparison or contrast is between the instability aspect. In case of truss, we know that if r is less than 3, it means that there are not enough number of reactive components to prevent a rigid body translation or rigid body rotation. So this is applicable directly to frame as well. Okay, so I need not explain further about this. Then the second aspect is regarding the internal instability. Okay, in a truss we said that when m is less than 2j minus 3, it means that there are not enough numbers contained in it to resist a local, say, relative rigid body rotation. Okay, that we have demonstrated already. So the same can't be actually, we can't just extend this idea here, because I have already told that the idea of triangulation is not applicable to a frame. But however, we can have an analogy here. In a frame, if any member contains or any joint contains excessive internal releases such as an internal hinge, in that case, what can happen is it can also lead to instability. We will understand this better when we relate this with an example. Okay, I'm not getting into this further. But the last aspect is what I can say is, in case of a truss, we said m plus r, if it is less than 2j, we said we don't have enough number of unknowns, but we have, I mean to say, we have more equations to be solved for less number of unknowns. In that case also, what we can mathematically say is we have undetermined set of linear equations, continuous equations. So it leads to instability because the problem what we are dealing with will not have a unique solution. The same is applicable here, but here we say when 3m plus r is less than 3j, that is 3m plus r is less than 3j, then in that case also we can say we have less unknowns but more equations, which causes instability. Okay, this helps, I suppose. And finally, there was another scenario where instability could be possible. That is when r is greater than or equal to 3. Okay, even if this is the case, if the support reactions or the members are not appropriately arranged, it can also lead to instability. Okay. Hope this, whatever details we have, is good enough to proceed with examples. Let's go to the first example. In this case, we have a simple frame where we can see that the numbers of reactions equal to 3. Okay. But we also see that the reactions are neither parallel nor concurrent, which means this frame is stable. Okay, that is the direct conclusion. Then we see that number of channels equal to 3 and number of numbers equal to 2. If we use this in the formula 3m plus r minus 3 gives a value of 0, which means this frame is statically determinate and stable. Further details I am giving here, I can't keep on saying the same information. So we see what is what here, what this 2 stand for, and what this 3 is for. For instance, this 3 is for the number of reactions such as HAVA. We are not going to explain it further. Just for completeness sake, I have included this here. Let's move on to the second problem. Here we see that R, J are both 4 and number of ones is equal to 3. So using the formula 3m plus R minus 3j, we get a value of 1, which means this frame is statically determined by a degree 1. Whether it is internal or external, that can be answered by seeing what is the value of SE, which is this external static indeterminacy. That can be determined using the formula R minus 3. That is, if we have more than 3 reactive components, it's going to contribute to the external static indeterminacy. So we see that S equal to 1 here. That means we have one excessive reactive component which causes external static indeterminacy. Okay, so this frame is stable and statically indeterminate by degree 1. Fine. Then we'll move on to the third problem that we see here. So here R, J, and M are all 4. So if we use the formula SC equal to R minus 3, we get a value of 1. Just a visual inspection makes clear that there is one excessive reactive component, which means the external indeterminacy is 1 in this case. Then we can use the formula as we have for S, which gives a value of 4. If we subtract S from SE, it gives what is SI, which is the internal indeterminacy, static indeterminacy. So if we use the formula, we see that SI equal to 3 in this case. That means maybe I will have to make a cut here. If I make such a cut, what does indicate is it means that there are 3 excessive internal stress resultants which can't be determined using just the equations of equilibrium. Okay. But I have one more method to demonstrate the same, that is to determine that S equal to 4, S E equal to 1, S I equal to 3. The method is called method of open tree. So what we need to do is, if we have a frame, we need to have the frame stand only on a fixed support. If we don't have a fixed support, we can induce them. I will let you know how. Then we also make sure that we don't have any closed loops. Okay, if we do so, we get something like an open tree. Okay, we can consider this open tree as statically determined. That is, once we know, say if I apply loads to this, we can determine the reactive components first, then I can have enough number of cuts across any number of interest, and then I can see what is the shear force, bending moment, and axial force containing each number. So the overall idea is we need to convert a particular frame into an open tree. When we carry out this particular operation, we will use certain numbers. Finally, we'll add them up. That will give you the value of internal indeterminacy, external indeterminacy, or the overall indeterminacy. Okay. So the procedure is as follows: the frame should stand only on a fixed support. If the fixed support doesn't exist, we will induce one. Then we need to cut all closed loops, and we also need to uh, cut the accessibility components to have a tree just with open arms. Finally, count or sum up all the numbers, that will give you the indication of indeterminacy, starting indeterminacy. Okay. So this is the formula. This is the problem we are going to take up again. Just that I'm going to explain this concept using 3 manners. Okay, so there is a just not a single way. There are 3 ways in which we can approach this, and we can establish the value of indeterminacy. First one is here. What I'm going to do is, we see that we have only 2 pin supports, but I told we need a fixed support. Okay, so what I need to do is, somehow I need to induce the fixed support here or here. What I'm going to do is, I'm going to induce it here in this first way. How do you do that? We can easily do that because we already know that in a pin support, 2 translation degrees of freedom are already restrained. But in a fixed support, what is additionally restrained is rotation. Okay. So to account for that, what I am doing is, I am deeming this as a fixed support by putting -1. This -1 is to account for the aspect that rotational degree of freedom also is arrested. So I am considering this as a fixed support. So this is done. What is the second step? I need to remove any extra reactive component. So I see that this is now the extra reactive component. So I need to remove that. As this is a pin support, I need to 2 reactive components. So I am putting a number 2 here. Okay. Finally, what else needs to be done? We see that this is a closed loop. So I need to cut it open somewhere so that it will become open. It will become an open arm. Okay. So I'm going to do that by cutting this number connecting the joint A and D. So when I cut that, what happens is there are three internal stresses written. So those three will be exposed here. That's it. Once we do that, we will get something like this. Okay, with a fixed support here. So this tree stands on a fixed support and it has all its. I have just one arm here which is open, or maybe two arms we can consider. So once we do that, that's all. Just we need to add these three numbers, which will give a value of 4. Okay, this is one way. But that's not the only way. I can do it otherwise also. The first two steps are one and same. I'm going to consider this as a fixed support by introducing -1 here, and then I'm going to remove these two reactive components. But earlier I cut this number, but this time I can cut across this number. Okay, in that case I can have something different like this. Okay, this is also a tree which is standing on a fixed support with its arm open. Okay, so this is not the only way. I can think of this way also. Even one can think of cutting this or this. Okay, it depends on one's personal choice. That's not the only way again. In these two cases, what I have said is I'm going to consider this as a fixed support. But in the third approach, what I'm going to do is I'm going to consider this as a fixed support. So I'm going to introduce -1 here. If I do so, the tree is considered to be standing on the fixed support here. Then the second step is I need to remove the excessive reactive components here. So I'm introducing a value of 2 here. Okay. Finally, the third step is similar. I should not have any closed loop. So I'm cutting this number here, which is connecting the joint A and B. So if I do so, three internal resultants will be exposed here. So that's all. I will have a tree something like this, which stands on a fixed support here. Okay. So that's all. Finally, I need to sum up these three values, which will give a value of 4. If you see carefully, we see that we got the same value earlier using the formula 3m plus r minus 3j. So overall indeterminacy is given by this. If I want to further categorize this as external and internal, what I can do is I need to be carefully observe how many external components add up. Okay, I mean to say if I just add the numbers pertaining to the supports, that will give you a value of external indeterminacy. Okay, in this case we can see that 2 minus 1 will give you a value of 1, which tells about external indeterminacy, whereas the number of cuts we introduce in terms of members, we need to count how many members we cut, and finally we need to sum them up and multiply by 3. Here I just cut one number in each case. So 1 into 3 will give a value of 3, which tells me what is the internal indeterminacy. Okay, that's all. I hope it helps. I have something similar here. We will take up this particular example in the upcoming video. We will introduce this idea and we will also use the formula and we will see how this works. Okay, so that is going to be interesting in the next video. By the way, thank you so much for the passion listening. Hope these concepts help. We'll meet again in the next video where we'll see more examples.